Hi everyone. Let's continue discussing chemical quantities, and today we're going to look at what are called empirical formulas. An empirical formula is just the lowest whole number ratio of elements in a compound. So, for example, ionic compounds, where we have two ions joining, their empirical formula is usually going to be the same as the chemical formula that we're saying, since ions always join at the lowest whole number ratio. So, for example, sodium chloride, NaCl, has a 1-to-1 ratio. These are the only ways that these two can join together, and so their empirical formula is the same as their chemical formula. However, where we really see empirical formulas come in is the use of molecular compounds. The empirical formula of a molecular compound may not be the true formula or the true molecular formula of it. Even if you simplify it, yes, the ratios are the same, but they're two completely different compounds. So, for example, CH4 versus C2H8 might appear to have the same exact ratio of atoms, 1 to 4 and 2 to 8. However, these are two completely different compounds, and such we have to treat them as two different compounds. So even though their ratios are the same, we cannot treat them as the same thing, and so the simplest whole number ratio here does not make a difference because of the fact that these are two completely different compounds. So it would not be correct to simplify the subscripts for one of these formulas to match the other just because their ratios can simplify into each other. Those subscripts indicate the ratio or the quantity of atoms within the compound, and these are the things that we want to look at when evaluating our empirical formulas. The mole ratio between the atoms can actually be used to determine the empirical formula, since taking ratios require us to use moles and not mass. So let's look at a few steps to go through in order to actually determine the empirical formula of a compound. So typically we want to work off of the fact that these elements are in a certain ratio to one another. These ratios can oftentimes be expressed through percentages or the percent composition. If we want to determine what these ratios are, we need to find out what the ratio of the moles are. And many times we are going to have a starting point of working with mass. However, if we're ever working with percent composition instead, then we'll need to find a way to get mass in order to begin our actual math conversions. So the first step that we should try to follow is, irregardless of whatever we're given, we want to assume that we have a 100-gram sample of whatever this compound is, so that if we don't have a mass, instead we have a breakdown in terms of the percentages of each element, we have a way to at least find a mass if we assume that we have 100 grams of the sample. By assuming we have 100 grams of the sample, we can now use this in order to find mass. Then, once we have mass, we can convert our mass into moles in order to begin our ratio or comparisons. So our second step is to convert mass to moles for each element in the problem. Once we have moles, we now have a way to find our ratios. Now, the smallest whole number ratio that there could be is a 1-to-1. So to ensure that we get the smallest value of our ratios to be a 1-to-1, we want to divide all of our moles by the smallest number of moles that we have. So we will divide all moles by the smallest quantity of moles that we already have. These ratios will usually be in some kind of whole number, and at this step, we can sort of begin to just round it off to a whole number. However, sometimes we will have to account for the fact that we might not have a whole number. In fact, we might have a 0.5 or even a 0.33, and we'll want to make sure that we account for that and multiply by whatever factor we need to get a whole number. So then that can be our last step, where we want to ensure whole number ratios by approximation or just scaling it ourselves with some kind of factor. So now let's take a look at some examples on how to calculate empirical formulas. So in the first problem, we have that a compound contains 74.8% by mass of carbon. The rest of this compound is hydrogen. We want to know, well, what is the empirical formula of the compound? So to begin, we know that this compound is at least 74.8% carbon. If the rest of that is hydrogen, and we know these two have to add up to 100%, that means we have 25.2% hydrogen in our compound. So the first step says that we need to assume we have 100 grams of the sample. So by assuming we have 100 grams, if 74.8% of that is carbon, then that is the same as having 74.8 grams of carbon. The same thing applies to hydrogen, that if 25.2% of my 100 gram sample is hydrogen, then I have 25.2 grams of hydrogen in the sample. Now that we have a mass, we want to convert these into moles. So we'll go ahead and divide by their molar mass. And by dividing by their molar mass, we are converting these mass into moles. So we end up with 6.23 moles of carbon and 24.9 moles of hydrogen. Now that we have moles of each element, to ensure the smallest whole number ratio being 1 to 1, we will take the smallest number between these two, which is 6.23, and we'll divide them both by 6.23. Here is where we either want to approximate to a whole number, or we want to get down to something that we can then scale up to a whole number. So in this case, this becomes 1, and this becomes approximately 4. So what this tells us is the ratio of carbon to hydrogen is 1 to 4. In our chemical formula, we know that we have carbon and we have hydrogen. So we essentially have these placeholders X and Y. That's where these 1 and 4 go in. It is telling you that we have 1 carbon and 4 hydrogens in our formula. So our chemical formula, our empirical formula, the simplified version, is CH4. Now let's take a look at another example. A compound contains 67.6% mercury, 10.8% sulfur, and 21.6% oxygen. What is the empirical formula? So we are 67.6% mercury, 10.8% sulfur, and 21.6% oxygen. Once again, our goal is to figure out what these subscripts are between mercury, sulfur, and oxygen. So we're going to go through our procedure again, first assuming that we've got 100 grams of the sample. So that means we essentially have 67.6 grams of mercury, 10.8 grams of sulfur, and 21.6 grams of oxygen. Converting these now into moles will get us our moles that we need in order to do our conversions. So for our mercury, we have 0.336 moles. We also have 0.336 moles of sulfur and 1.35 moles of oxygen. We will take the smallest number and divide them all. Our smallest number here is 0.336. This gives us 1, this also gives us 1, and this gives us about 4. So this tells us that we have 1 mercury, 1 sulfur, and 4 oxygens. Here is our empirical formula for this mercury sulfate from the problem. Now, in the case where we are not getting a whole number in the end, let's say that we ever end up with a 0.5. We must turn this into a whole number by scaling it up with some kind of factor, like by multiplying by 2. if we're given a 0.33, that just means we have to multiply by 3 to get a whole number. So if our approximations are too far for us to go ahead and make it into a whole number to round, then sometimes we'll have to multiply by some kind of scale factor, and that would apply to each of the elements then. Now, the empirical formula is the simplified formula, but it may not very well be the true formula. That is what a molecular formula is. It is the true formula of the compound, and it is equal to the empirical formula by some kind of whole number ratio. It could be the same as the empirical, or it could just be some multiple of the empirical formula. So the empirical is oftentimes just a reduced version of the molecular formula. Let's take a look at these examples to show the relationship between empirical and molecular formula. So in example A, our formula is C5H10O5. We can see here that we can actually reduce all of these by a factor of 5 and simplify it down to C1H2O1. This would be our empirical formula, whereas the original would be our molecular formula, because that is the true formula of it. In example B, C6H12O2 reduces down to C3H6O. So this one we reduce down by a factor of 2. In example C now, if we're looking at our subscripts 12, 17, 1, and 1, well, these cannot be simplified down anymore. So in this case, the molecular formula would be the same as the empirical. We see the same in D, where 2 and 5 cannot be further simplified, and so again, the molecular is the same as the empirical. In order to determine the molecular formula from the empirical, we need a little bit of information. Since the fact that the empirical formula is just some reduced factor of the molecular formula, we can infer that their masses also share this factor. So whatever multiple the molecular formula is in the subscripts to the empirical, the mass must follow suit by that same exact factor. So we can use the molecular mass of the compound and its empirical mass to figure out what that whole number multiple is, and then we can apply that to the empirical formula in order to find the true molecular formula of a compound. So let's see some examples of where we have to determine the molecular formula. So in this example, we're told that two compounds share an empirical formula of CH. Compound A has a molar mass of 78 grams per mole, whereas compound B has a molar mass of 26 grams per mole. We want to find the molecular formula of each compound. Now we're told here that these compounds have the same empirical formula of CH, which means that they are both some kind of whole number multiple of this formula. We don't know what that multiple is, but we do know the masses of each, and we can use that to help find out what that multiple is. So if we look at the formula of CH, this has a mass of 13 grams per mole. Since their formulas and masses would share the same whole number ratio, we can use the masses with the empirical mass to figure out what this ratio is. So for compound A, we know it has a true mass of 78 grams per mole. Compound A, and we will divide that by the empirical mass of 13 grams per mole. Dividing these two gives us a factor of 6. So that tells us that compound A is 6 times greater than the empirical formula. So that means compound A is C6H6. For compound B, we will repeat the process, taking a molar mass of 26 grams per mole, dividing it by the empirical mass of 13 grams per mole, giving us a factor of 2. So that means compound B has the molecular formula of C2H2. So there you have it. If you know the empirical formula, determining the empirical mass and finding the ratio with the molecular mass would give you the same ratio that their compounds share. So let's take a look at just one more example. We find here that a compound which has a mass of 7.36 grams has decomposed to give 6.93 grams of oxygen. The rest of the compound is hydrogen. We're told the molar mass of the compound is 34 grams per mole, and we want to find the molecular formula. So in order to find the molecular formula, we must know what the simplified empirical formula is. Now here we are not given, but we are given some masses. So we can use these masses to find the empirical formula by going through our process. In the first two empirical formula questions, we were starting off with percentages and assumed 100 grams. That is because we didn't have a mass to work off of. Here, we are given masses already, and we know that we have 6.93 grams of oxygen, and we know the rest of this is hydrogen. So that means out of the 7.36 grams, if we remove the 6.93, that is oxygen, we have 0.43 grams of hydrogen. We continue with our process of converting our grams into moles. And then once we have these moles, we can go ahead and find that ratio. So this gives us 0.433 moles of oxygen and 0.426 moles of hydrogen. We divide them both by 0.426, and we get a 1-to-1 ratio. So that means our empirical formula is OH. We can then go ahead and find the empirical mass, which is 17 grams per mole. Since we know the true mass is 34, we would take 34 divided by 17, and that is a factor of 2. So our molecular formula would be double the original, and just written in the correct order, it would be H2O2. So we can see here the empirical formula, which we determined by going through our steps from before, and then what the true molecular formula would be. So we follow this process in order to find molecular formulas, knowing that sometimes they can be the same as the empirical, but oftentimes we need to find out what that whole number multiple is, and we can use their masses for that.